In this class, let's understand the important derivations of EMF of the cells in different combinations. Before going into derivations, it's better to recall some basic concepts which you have already learned. Take a cell. Take a cell. A cell is represented by like this. Take a cell of EMF E, and the cell drives a current in the external circuit. External circuit. And it is found that no work is done when the current passes through the copper wire, because copper wire has very low resistance. It doesn't offer any resistance to the flow of the current. Hence the cells no need to spend any energy to drive the charges through the copper wire. But when the copper wire is connected to some alloys called as the resistors, the cell has to do some work. The cell has to do some work to drive the charges. The work done by the cell to drive the 1 coulomb of charge from, say, one end of the resistors A to B is represented as a potential drop across the resistor. Potential drop across the resistor. Let I be the current. That means the charges flowing per second is maintained in the circuit by the cell. Yes. It is found that even the cell also has some resistance, because inside the cell there are many chemicals. Like these chemicals are not good conductors of electricity. They also offer some resistance to the flow of the current. That resistance is represented by a small resistance mark near the cell. A small resistance mark near the cell. It is represented by the letters small r. Again here, the cell has to do some work. The cell has to do some work in driving the charges inside the cell. Let the work done be V dash. Let the work done be V dash. Yes, now we have taken a cell of EMF E and internal resistance R connected to an external resistance of external resistor of resistance R. Okay, and V is the potential drop across the external resistance. V dash is the potential drop across the cell, inside the cell, across the cell. By the definition of EMF of a cell, by the definition of EMF of a cell, EMF of a cell is nothing but work done in sending or driving 1 coulomb of charge. 1 coulomb of charge from one end of the cell to the another end in the external circuit. Work done in sending 1 coulomb of charge in the external circuit. In this case, that EMF is equal to the work done in sending the 1 coulomb of charge. Work done in sending 1 coulomb of charge. In sending 1 coulomb of charge from A to B plus work done in sending the same 1 coulomb of charge inside the cell. Yes, from negative terminal to positive terminal. So therefore, we can write the total EMF of the cell is equal to the work done in order to drive a unit positive charge from A to B. That is represented by the V and V dash. V is called as potential drop across AB. V dash is the potential drop across the cell. So the potential drop is nothing but the work done by the cell to drive 1 coulomb of charge in the external circuit and inside the cell. Ohm's law gives the relation between external potential drop V and the resistance of the alloys wire resistor as V is equal to IR. Therefore, we can say that EMF of the cell can be written as I into capital R. Similarly, the I into small r, where small r is the resistance of the internal resistance of the cell. This equation can be used to calculate the expression for the current in the circuit. Take the I common factor, we will get R plus small r. Now divide throughout by R plus R, cross multiplying EMF. Even though we write epsilon, we read it as a E, or simply we call it as a EMF of the cell. EMF of the cell. Divided by R plus R. So that is the expression for current in the external circuit. This is already we might have learned in the previous classes. But here, the equation what we are going to use for our derivation is E is equal to IR plus I into small r. That EMF of the cell is nothing but IR. Instead of IR, we can say potential drop in the external circuit plus I into small r. And shift this IR to the left side. Therefore, it becomes epsilon minus I into R is the V. So in our derivation, we use the potential drop in the external circuit, in the external resistance, V, or the potential drop from one point to the another point as EMF of the cell minus I into internal resistance of the cell. So this is the equation which we are going to use in our derivation. So therefore, this equation is very important. So V is equal to EMF of the cell minus I into small r. Okay, students, this is the basic information that's needed for our further derivations. Okay, yes. So here I kindly request you to subscribe my channel so that new videos will reach you and you will be greatly benefited. So purposely I am teaching slowly, so that the average students can follow it. Okay. Let's go ahead. Okay, students, let's derive an expression for equivalent EMF and equivalent resistance of two cells connected in series. What's the meaning of two cells connected in series? Let's take a cell. Let's take a cell of EMF E1 and internal resistance R1 and connected in a circuit between the points A and B. Between the points A and B. Now let's connect another cell with the internal resistance E2, with EMF E2 and internal resistance R2 between the 2 points A and C in the circuit. Let these two cells drive a current I in the circuit. Let they drive the current I in the circuit. Let these cells drive a current I in the circuit. Now the two cells are connected end to end, and this connection is said to be cells connected in a series. And it is found that this combination is equivalent. This combination is equivalent to a single cell of EMF, let us represent it as a E equivalent, and the internal resistance R equivalent, connected between the same points between the A and the C, that drives the same amount of current I in the circuit. So instead of the two cells, connect a single cell of EMF equivalent and internal resistance R equivalent. That cell should drive the same current in the external circuit, same current I in the external circuit. Yes. Now let's apply some of the equations we have learned earlier. It is found that let us assume that let the potential drop between A and B be VAB. Let it represent as VAB. And potential drop across the cell, second cell, let it be VBC. And the total potential drop between the points A and C, let it be VAC. And even in second case also, let the potential drop between the points A and C be VAC. By using the equations that previously learned, we can write that the potential drop AC in the combination can be written as the sum of the potential drop across the points AB and the potential drop across the points BC. And because the I is the current passing through it and EMF is E1 and R1 across AB, we can write that V as the epsilon 1 minus I into R1. Similarly, across the second cell, VBC can be written as E2 minus I into R2. So therefore, VBC is nothing but epsilon 2 minus I into R2. You can just slightly rearrange this equation. So as epsilon 1 plus epsilon 2, take the minus common factor, we can just minus I common factor, we can write I into R1 plus R2. Let this be equation 1. Similarly, for the equivalent cell, for the equivalent cell, we can write here that, so VAC can be written as E equivalent minus I into R equivalent. Okay, V equivalent minus I into R equivalent. Yes. So let's write the same thing here. So potential drop across AC in the equivalent, the cell can be written as E equivalent minus I into R equivalent. I into R equivalent. Let that be equation 2. Equation 2. By comparing the two equations, because left hand side is same, we can write that by comparing, we can write that E equivalent of the combination can be written as the sum of their EMFs. Sum of their EMF. And these R equivalent can be equated to the sum of their internal resistance. Therefore, R equivalent can be written as the sum of their equivalents. So this is the derivation of the, okay, this is the derivation of E equivalent and R equivalent when two cells are connected in series. Similarly, when three cells are connected in series, you can just write E equivalent is equal to sum of their EMFs. Sum of their EMFs. Okay. Similarly, R equivalent is equal to sum of their internal resistance. Okay. Sometimes, if the cells are connected in such a way that if one of the cell is driving the current in opposite direction, let us assume that the first cell E1 of EMF E1 is driving the current in same direction, but the second cell is connected in, okay, such that it is driving the current in the opposite direction. And let's connect another cell which drives the current, okay, in the same direction as the first cell. So in this case, if the negative terminal of the second cell is connected to the negative terminal of the first cell, okay, here the second cell is sending the current in opposite direction. At that time, so you should remember that, okay, equivalent EMF of such a combination is written as E1 minus E2 plus E3 plus E3. So when the any cell is connected in a reverse manner such that it is driving the current in opposite direction as the remaining cells, so that EMF we have to put a minus sign. A negative sign should be given to that EMF of the cell. Okay. That's it, students. Thank you very much for watching, and please don't forget to subscribe, and your subscription is well appreciated, and it is greatly required for me to put more videos. Thank you very much.